Hello everyone. In this lecture, we are going to see about this multi-core and other shared memory multiprocessors. So what is shared memory multiprocessors? Shared memory processors or multiprocessors is one that offers the programmer a single physical address space across all processors, which is nearly always the case for multi-core chips, although a more accurate term would have been shared address multiprocessor. Processors communicate through shared variables in memory, with all the processors capable of accessing any memory location via the loads and store instruction. So this is the classic organization of the shared memory multiprocessors. These systems can still run independent jobs in their own virtual address space, even if they all share a physical address space. So here there are two styles. In the first style, the latency to a word in memory does not depend on which processor asks for it. So such machines are called Uniform Memory Access Multiprocessors or UMA. In the second style, some memory accesses are much faster than others depending on which processor asks for which word, typically because main memory is divided and attached to different microprocessors or to different memory controllers on the same chip. So such machines are called non-uniform memory access multiprocessors. As you might expect, the programming challenges are harder for an NUMA multiprocessor than for a UMA multiprocessor, but NUMA machines can scale to larger sizes and NUMAs can have lower latency to nearby memory. So this is about the terms that are synchronization and lock. As processes operating in parallel will normally share the data, they also need to coordinate when operating on shared data. Otherwise, one processor could start working on data before another is finished with it. This coordination is called synchronization. When sharing is supported with a single address space, there must be a separate mechanism for synchronization. One approach uses a lock for a shared variable. Only one processor at a time can acquire the lock, and other processors interested in shared data must wait until the original processor unlocks the variable. So this is a simple parallel processing program for a shared address space. Suppose we want to sum the 64,000 numbers on a shared memory multiprocessor computer with uniform memory access time. Let's assume we have 64 processors. The first step is to ensure a balanced load per processor. So we split the set of numbers into subsets of the same size. We do not allocate the subsets to a different memory space since there is a single memory space for this machine. We just give different starting addresses to each processor. So Pn is the number that identifies the processor between 0 and 63. So this is the program. All the processors start the program by running a loop that sums their subset of numbers. So if you see here, this is sum of Pn which is equal to 0. This is the processor array. Then for I is equal to 1000 into Pn, I less than 1000 into Pn plus 1, then I plus is equal to 1. So what we need to do is that we need to increment by 1. So sum of Pn plus is equal to A of I, that is the sum the assigned areas. So the next step from this is we need to add these 64 partial sums because we have got the 64 sums from the 64 processor, and this step is called the reduction where we divide to conquer. So this is the hierarchical nature of this reduction. Half of the processors add pairs of partial sums and then a quarter add pairs of the new partial sums and so on until we have the single final sum. And the last is this private variable. In this example, the two processors must synchronize before the consumer processor tries to read the result from the memory location written by the producer processor. Otherwise, the consumer may read the old value of the data. We want each processor to have its own version of the loop counter variable I So we must indicate that it is a private variable. So here's the code, and here if you see here, this half is the private. Thank you.